Hello, welcome to ISAT430 Materials and Manufacturing Processes. This is lecture 10, Particulate Processing of Metals and Ceramics. All right, so first, we're going to talk about one technology that is powder metallurgy. What is powder metallurgy? Powder metallurgy is a technology, so it means that we are making parts or making products out of metallic powders. So usually, when we're making those kind of products, the first process is to press or form those powders into a certain shape, and then sinter the small powders and bond the powders into a bonded shape, and then we can create our product. So there is a video. It talks a little bit more about details of metal powder. It also gives some visual aids about this. I suggest you watch this video, and then we can continue the slides. While we are making using metal or powder metallurgy to make products. So there are a lot of reasons. So there are two main reasons. So one is that sometimes we want to make some products that with a good level of porosity. Why? Because sometimes those porosity can actually help the function of the products. For example, bearing and gears. So those bearing gears, they a lot of times they are oil lubricated, and so those porosity or pores actually can store those oils, so better to be lubricated in their function. So those kind of products is a very good example for powder metallurgy application. Well, another one is sometimes it is a little bit hard to make really high strength or hard materials, tools or products with high strength materials. Well, in this case, because we cannot find very high strength tools to machine them. In this case, we had to find out another method to create those kind of tools. So that is why we are using metal, powder metallurgy to create those. Of course, this kind of technology has some limitations. For example, usually it's the process is very high cost. One reason is the high tooling and equipment cost. Another reason is because we are dealing with metal powders, so making of the metal powder itself actually is a complicated process, and also it requires extra process in order to make really good shape or quality of the powders. That's why it's very expensive, and also the metal powders are not very consistent in shape and sizes, and also geometry. In order to if you want to control the geometry of those, you also need a very good equipment, and also high accuracy of the equipment in order to make sure those geometries of the of all these powders are consistent. Some of the working materials for powder metallurgy, it can be alloys of iron, steel, and aluminum, and some other metals can be copper, nickel, or some other refractory materials such as molybdenum and also tungsten. And metallic carbides, such as tungsten carbide, are often included within the scope of the metal powder metallurgy as well. So you can see some of the examples that made from PM. So those are this can be created by this technology. First, if you want to know more about powder metallurgy technology, first we need to understand the powders. So how the powders function, or what are their characteristics in manufacturing processes. First, in powder metallurgy, the engineering powders are usually metals or ceramics, and their geometries, features we are looking at are particle size and distribution. So, and also particle shape and internal structure, as well as surface area. Now let's first look at what is particle size. The particles can be big or small, but how do we measure the size of the particle? So one measure is to use mesh count. So mesh count means it's a number of openings per linear inch of screen. For example, it's a mesh count of 200 means there are 200 openings per linear inch. So you can tell that in this whole area or this whole square of 200 openings of 1 linear inch, you can find out how many particles they can actually hold. For this one, it will be 40,000 particles. So this is the mesh count. So if for 1 square inch, the more particles you can hold, actually the smaller particle size it is. You can see the comparison of the picture here. And there are many different particle shapes in powder metallurgy. For example, the spherical, rounded, spongy, and flake or cubic, some other shapes. They all can be created from the process. And so because the powder actually have different shapes and also sizes, so when you are mixing them together, actually they're gonna have a friction between particles, and the friction actually matters in the flow of the process, in the flow of the powders as well. So there's a way to measure the friction of those. The measure is called angle of repose. So angle of repose means if you use a funnel and to pour the particles onto the ground, it will start to create a pile of powders, and the angle is the repose is that angle. So which means that if the friction between the particles actually is big, what happens is the angle of repose is actually a little bit bigger. This angle will be bigger, right? So larger angles usually mean that greater interparticle friction. And of course, smaller particle sizes generally show greater friction and steeper angles. The reason for that is, the smaller particle sizes usually have larger surface finish for interactions or interparticle friction. So that's why you usually have a greater friction. And spherical shapes have the lowest interparticle friction. When the shape deviates from spherical, actual friction between particles will tend to increase. So these are some of the points you can go through. And if you want to reduce the interparticle friction, you can add some lubricants. Another character for the powder particles is particle density. So particle density, there are two concepts. One is true density, and the other one is bulk density. So true density means that's the density of the true volume of the material. So what is the true volume of the material? That means that if the powders are all melted into a solid mass, so in this case, what happens is there won't be any a lot of gap or pores between those particles, and it will form a kind of solid shape. So this is called true density. While the bulk density is the powders in a loose state after you pour all the powders there. So that's a bulk density. And if we use a bulk density divided by the true density, we'll get a packing factor. So we sometimes use the packing factor to describe how loose the particles of the raw materials is, and also what is the porosity of those. And typical values for loose powders are 0.5 to 0.7. And if powders of different sizes are present, and smaller powders can fit into the spaces between larger ones, it will usually will create a higher packing factor. And because they're in a loose state, so if you evaporate the powders, sometimes you can be increase the packing factor, because it causes those kind of particles actually to settle in a more tightly state. Of course, if you press them and compact them of the powders, you can also increase the packing factor. And so using the porosity plus packing factor actually equals to 1, because porosity is a space that is created from the loose of the powders. So metallic powders are usually classified as either is elemental, so which means it's a pure metal, or is a pre-alloyed, so means that each particle is on alloy. And some of the possible surface films include oxides, silica, or absorbed organic materials, and moisture. Of course, those kind of films actually can be removed, from the powders before it can be shaped. And for making of the powders, usually that's a separate operation. So what the manufacturer will do is they're gonna buy the metal powders from a supplier, and then they'll start to make the product from those metal powders within their house or within their shop floor. But the powder making the powders usually is from a different supplier. And what are those processes for making those powders? And usually there are 3 main processes: atomization, or some of the chemical methods, or electrolytic methods as well. So typically, any kind of the metal, it can be made into powder. First, let's look at atomization. So what is atomization? It can be gas atomization method, or it can be water ones. So what it means is that, well, we have a molten, for example, in this picture, we have molten metal, and by pressure we can have this molten metal to flow upwards, and then meanwhile we give a gas to blow or spray to the molten metal into a chamber. So when we are spraying this with the molten metal, it will start to form those small particles. So this is a way to create those metal powders. And you can watch the video in this slide to see what is the process in industry, how it looks like. Another method is the water atomization method. So the difference between the gas atomization method is that here we are using the water to spray and to wash to create that kind of a blowing power to create those metal powders. And for the sequences of making products from metal powders are usually the first process is to blend and mix the powders together, and then I'm going to compact them into a certain shape. So after that, because those shapes, actually there are a lot of pores, porosity is high, so we'll also need to sinter them so that all the particles will start to bond together. And sometimes, some secondary operations might happen in order to increase the dimensional accuracy or density. First, blending and mixing of metal powders. So blending means the powders of the same chemistry, but possibly from different particle sizes, are intermingled. And mixing means that powders of different chemistries are combined. And next, the compaction, during compaction stage, so it means we are using higher pressure to the powders to form its shape. And so usually we call it pressing, right? For example, you can see a pressing machine to create that, to use a die and then press that into a certain shape, and then after that we call that it's green compact after it's compressed. So that's and so this is the machine for the example of machine for conventional pressing. So first, we fill the die cavity with the powders by automatic feeder, and then it will start to give initial power to it, and then we'll start to give a higher power of the punch into the die, and then create the shape of the powders or shape of the product, and then the part will be ejected. So after this process, the part you get is it's compacted powder or particles, but there are a lot of gaps between particles. So the next process will be to sinter them, or start to have all the particles start to form the bond between each other. And of course, when we are sintering the part, what happens is that we are not gonna heat it up at a very high temperature to melt the metal powders. So we have to keep the temperature below the metals melting temperature. Otherwise, it will be melted into a liquid stage. It loses its form or shape. And during the sintering process, we should know that the part is actually going to reduce its size because of the shrinkage. So when we are sintering, means actually when the particles are starting to bond with each other, actually it will it will getting closer and closer. So that's why the whole part will getting a little bit smaller, and also the pores are getting rid of. So you can see from this picture to look at that the stages or the process or the sequence of sintering and how the gaps or the pores actually disappear or get reduced from sintering. So at the beginning it will start to have a point bonding, and then later it will start to form some necks, and then further it will you can see the pores actually getting smaller and smaller. Eventually we'll see more boundaries between those kind of particles. We call it grain boundaries. And what kind of equipment for sintering? So usually there is a sintering furnace, or is a chamber that is heated environment, and there's a belt, so it could go through it. You can see from this picture, there's a preheat into a certain temperature, and then also there's a sintering stage for a little while. So that's your sintering process will have is a higher temperature, and then later after it's sintered, it will start to cool down of the part. So you can use this kind of a conveyor belt to move the parts and also to sinter them. Some kind of secondary operations are also performed on sintering sinter part to increase density, improve accuracy, and also accomplish additional shapings. Those can be repressing. So make sure repress it into a closed die to increase density and also improve some of the properties, for example strength, and also sizing. to make sure that the product we created actually have a good dimensional accuracy, because after shrinking, originally we are making the green compact. What happens is we are giving a lot of compensation for shrinkage, so maybe it's a little bit oversized, but after centering, we actually can resize it in order to make a better dimensional accuracy. And also cornering, pressing details into its surfaces, of course machining as well if we need it. And so porosity is sometimes we do not want porosity, but also sometimes in manufacturing or in some industry we need porosity, and also there are ways to utilize the porosity to create new products with special characteristics. For example, one is impregnation, and the other one is infiltration. Now let's look at each of the process. So impregnation means that we are filling the pores with oil or some other fluid. For example, we are making gears or bearings. We want a lubricant or some oil to get into the pores, and so that those lubricant can be stored in there when those parts are functioning in industry applications. And so that is make those for lubrication purposes. So that's the impregnation. Well, infiltration means we are filling those pores with metals, right? With molten metal. So usually the metal that is going to fill that pores is called a filler metal. And some alternative pressing and also sintering technologies. So because some of the conventional press and the sintering sequence is the most widely used shaping technology and powder metallurgy. Some other ones are such as isostatic pressing, powder injection molding, and also powder rolling, extrusion, or forging can also make those powder products. Powder rolling, you can see from this picture, we have a feedstock of powders, and then we'll go through two compaction rules, to create this kind of compaction power to form a green strip. But those kind of green strip is kind of a little bit loose shape that needs to be sintered in order to create a better bonding between particles. And then after that, it will go through a cold rolling mill and also a resintering furnace in order to create a better dimension of the parts. So for the raw materials and some of the products we made from the powder metallurgy, the raw materials for powder metallurgy are more expensive than for other metalworking because of the additional process that is needed, and also the additional energy that is required to reduce the metal to a powder form, right? And some elemental powders, the pure metal in particle form, and some of the common elemental powders include the iron, aluminum, and also copper. And those elemental powders can be mixed with other metal powders to produce alloys that are difficult to formulate by conventional methods, such as some of the tool steels. Also, we can use pre-alloyed powders. So pre-alloyed powders means each particle is the alloy. So some of the typical pre-alloy powders, such as stainless steels or some copper alloys or high-speed steels. In this case, we do not need to manipulate the character of the or property of the products after it's made. We can actually just use those raw materials as already alloyed powders and to create the shape of the product we want. Some of the typical products we already mentioned actually the gears, bearing, also sprockets, fasteners, electrical contacts, cutting tools, and many machinery parts can be made from powder metallurgy. Those kind of have very typical characteristics. Either they need some of the poor porosity for their products, or they have very special character strengths or a property that is required in their working environment. All right, so there are some of the quiz questions I'm going to go through. So then we're going to look at processing of ceramics and also cermets. So ceramics usually can be categorized into three different categories. So one is traditional ceramics, and also another one is new ceramics. So traditional ceramics are usually made from the minerals occurring in nature. Some typical products like pottery, it has been a long history, and also bricks or cement. And some new ceramics will be the powders or raw materials are made from synthetic processes, and the products are more for special uses, such as cutting tools, artificial bones, or nuclear fuels, those kind of applications. Of course, there's another category of ceramics is glasses. So starting material for those particularly processing is always the powder. So for traditional ceramics, and the powders are mixed with water to bind them together and to achieve proper consistency for shaping. While for new ceramics, they're not using water. Right? Instead, they are using some of the binders in order to create those kind of binding or shaping. So after shaping, the green part same has to be sintered, because it's all our particles, our powders, so they have to be sintered in order to create those kind of bonding. And so the typical process for traditional ceramics, it's kind of similar to powder metallurgy. So first we prepare the raw materials, make sure they are the particles are consistent, and also then next is to form those particles into a certain shape, and then we're going to dry it. To dry means that's evaporation of the water, to let the part of the product sit in a while so that some water can evaporate. And then after dried, you can see the gaps or the pores between in the part actually start to disappear, but there's still a little bit some left, and also the bondings between the particles is very weak. Then when it goes through a ferroring process. Ferroring process means we are getting all the pores, and also to formally start to create the kind of bondings between the particles of those for ceramics. And for preparation of raw materials, most of the shaping process for traditional ceramics require the starting material to be plastic paste. So plastic paste means that is ceramic powders that is mixed with water, right? And those kind of ceramic powders actually it can be seen very commonly seen in nature, like rocky lumps, right? So these are very typical one, and then we can grind them or reduce the size of those into the one we need. So how to reduce those big rocky lumps into small sizes? There are two different type of operations. So one is the crushing, and another one is the grinding. And the academic name for reducing the particle size is called comminution. Right. So here are two pictures or examples. You can see the difference between a crusher. So the left one is the roll crusher and the right one is a jaw crusher. You can see how the bigger sizes of the raw materials actually can be crushed into smaller sizes. Another process is the grinding. So the grinding means we are using some of the small mills in order to grind them into very small particles, small shapes. It can be a roller mill or it can be a ball mills. You can see the differences between the ball mill and also a roller mill. You should also watch the two videos so you can see how actually it works in more vividly. For preparation of the raw materials, and the main ingredients of ceramic paste is clay, water, some of the non-plastic raw materials, and also some ingredients in order to enhance the properties of the of the part. So for the clay, you can see this chemistry formula or material. Usually that's hydrous aluminum silicate, and also some of the non plastic raw materials. It can be alumina or silica. So the purpose of adding non-plastic raw material is to reduce the shrinkage in drying and the fairing, but also reduces plasticity during the forming. And for the shaping process of ceramics, there are several processes. One is slip casting. So slip casting means we are creating a clay water mixture as a slurry, then to create the shape using the slurry into a die. And also there's a plastic forming method I'm going to talk about later. Some of them are dry, semi-dry pressing, and also dry pressing. And you can see from this graph, you can look at how those kind of processes actually are dealing with water content. For example, dry pressing means we are not going to use any kind of water in the mixture of the raw materials. So in this case, what happens is it will not have a lot of porosity in the product. And if the slip casting means we need to add a lot of water, so that means that we're also going to start to lose a lot of size or shape when we are centering the products. First, slip casting. So slip casting is a suspension of the ceramic powders in the water is called a slip, and we pour that slip into a porous plaster of Paris mold. Right, so you can see from picture 1, we pour that into a mold, and then it will start to form a layer at the surface of the mold, and then we're gonna pour the extra slip out. Then later we will start to form this kind of shape of the same shape as the mold. And so usually the slip composes 25 to 40% of the water. You can watch this video to see how others are using slip casting to make a shape of the product or a vessel or something. And for the plastic forming, it can be manual methods, or it can be mechanized methods. Some of the manual methods will be the hand modeling. So hand modeling means we're using our hands to form the shape of the plaster, and also we can also form that with jiggering, use jig with a jig, or we can do plastic pressing to use a press to form the shape, or use extrusion to form the shape. So you should watch those videos so you can see for each of the shaping process what it look like in industry, and also what kind of type of products it can be made from those process. For example, extrusion. Right? Extrusion, maybe it can make some of the long tube shaped or T-shaped beams from those materials. Another type of process is semi-dry pressing. So semi-dry pressing means we deposit moist powder in the die cavity and also press it with very high pressure. Then after the die, then we open the die and also eject the part. Next one is dry pressing. So dry pressing means we're dealing with the mix with very little water. So usually the water content is probably less than 5% of the mix. Advantage of using dry pressing is that there's no drying shrinkage occurs, right? So we can achieve really good accuracy in the shape. Some of the typical products from dry pressing will be bathroom tiles, electrical insulators, or refractory brick, or some other simple geometries. So this is a graph. You can see how during the shrinkage actually how the volume of the wet clay changes. Then drying. For drying, the drying process occurs in two stages. So stage one, so drying rate is rapid as the water evaporates from surface into surrounding air, and also the interior water migrates by capillary action to surface to replace it. So this is the volume will start of the part will start to shrink, right? And also there's a little bit of risk of warping and also cracking when the part is losing water. While the stage two, the moisture content has been reduced to where the ceramic grains are in contact. So which means there's little or no further volumetric shrinkages will happen. And you can see from this graph that how when we're looking at this graph, actually we are looking at it from right to left, right? So that's the process of drying. So first part is the drying cycle, right? So it's that is stable line. And then the next stage is during the second stage of drying, you can see how the volume actually decreases. All right. So next, fairing and glazing. So fairing is heat treatment to sinter the ceramic materials. Usually it's performed in the furnace. It's called a kiln, and bonds are developed between ceramic grains. And glazing means we can actually apply some of the ceramic surface coatings to make the piece more charming or looks good, and also prevent the water to get in. So for the new ceramics, the manufacturing sequence is pretty much the same as traditional ceramics. Also include preparation of starting materials, shaping, sintering, as well as finishing. But for creating new ceramics, actually they usually requires higher, more strict parameters or accuracy in each of the steps. So it means that we'll need a greater control, not only in for the starting potters, but also in each of the process. For example, mixing, sintering, and as well as secondary processes after that. For shaping of the new ceramics, many of those processes are actually similar to potter metallurgy. We can do press, right? Use a press to shape them, and also sinter them together. The same method can be applied to new ceramic materials. Also, some of the traditional ceramics, some of those kind of traditional ceramics techniques can also be applied into new ceramics manufacturing. For example, slip casting, we just talked about, extrusion, and also dry pressing also works for new ceramics. And some of the processes include the hot pressing, isostatic pressing, doctor blade process, and also potter injection molding. So I suggest you can look at all these processes either in the YouTube videos or in look at some of the picture of those, so you can see how these processes actually are practiced in industry. For example, the doctor blade process is actually to create a very thin film from new ceramics. And the next process is the sintering. So because the plasticity needed to shape the new ceramics is not normally based on water, so the drying step required for traditional green ceramics is omitted for most of the new ceramic products. And it's so sintering step is of course required, and the functions of sintering are usually the same as before, to bond the individual grains into a solid mass, or increase density, and also reduce or eliminate porosity. For finishing of the new ceramics parts, usually we apply some secondary processes to either to increase the dimensional accuracy or improve some surface finish or make some minor changes in part geometries. And finishing usually involves abrasive processes in order to create a better surface finish. So Derman abrasives can be used to cut those kind of hardened ceramic materials. And for cementing carbides, so cementing carbides is a family of the composite materials consisting of carbide ceramic particles and also embedded in the metallic binder. So it has both carbide ceramics particles and also some metal in it. And some of the binders, such as cobalt, it works best with tungsten carbide, and the binder metal for percentage of the binder metal is usually 4% or up to 20%. And so the powders of the carbide and the binders usually thoroughly mixed together. Mix the wet in the ball mill and to form a homogeneous sludge. And for processing of cermats, that is, we use compaction to make them. So usually the process is the cold pressing. When we're doing that, and usually we have to make the dies that is with a little bit oversized to account for the shrinkage during the sintering. And if it is a high production, so the dies are usually made with tungsten cobalt liners to reduce some of the wears. The next is sintering of the cermets. You can see this graph. It shows a phase diagram of the tungsten carbide and cobalt at different temperatures. And so we are sintering tungsten carbide without metallic powder. It will result in material is less than 100% of tooth density, right? Well, if we use a binder, it actually can create a free porosity for the product. So that's why we are using a binder. Some of the secondary operations for making cermets. Grinding, for example. So we can grind them with a diamond or bristle wheel to create a better surface finish, or required accuracy of geometry. So some other secondary operations for shaping include electric discharge machining. So EDM is also a very typical machining process in advanced manufacturing, and also ultrasonic machining as well. You can watch the video about ultrasonic machining from this slides. All right, so these are the questions for processing of ceramics. And that's all for this lecture.